Just to give kind of like a brief introduction, I'm Peter. I'm the co-founder and CEO of Aquarium. And previously to this, I was at Khan Academy and Pinterest doing kind of like machine learning for web stuff. And then I did some research at Berkeley on deep learning for object detection back in the sort of bad old days when, the framework of choice was Cafe, and everyone was kind of like forking stuff off of it to get the stuff done. And then took some of my research to Cruise, where I was a pretty early employee there, helped build out the computer vision, deep learning stack there over time, and then got to the point where eventually we went and got acquired by GM, and you can see a bunch of Cruise cars driving around San Francisco right now. So that's kind of my background. And in terms of the motivation for this talk and for the company that we're doing right now, basically background is that when you look at kind of the old school sort of wave of machine learning, stuff that you can see as like, search ranking, recommendations, or things where the sort of web companies like Google and Facebook kind of pioneered in like the early and mid 2000s. Like, you had this paradigm of machine learning where data kind of came for free. So like the sort of like machine learning tasks were to predict what people would click on, or it would be to forecast what would happen in the future. And it turns out with both of these things, like, people naturally click around your web app and give you data. And you kind of can see what happens in terms of the accuracy of your predictions as you kind of wait in time. Like, trying to predict the stock market, and then you actually see how it does, and then you can use that to correct your model. And so in that sort of era of machine learning, that was all like logistic regression and, like random forest and all that, like that, most of the leverage was actually in, number one, like making sure that the data pipelines could scale to a lot of like mostly structured data. And then number two, working on the model, doing like feature engineering on the structured data, because that was kind of like where a lot of the gains could be gotten. And now when you sort of look at deep learning applications where you're working on imagery, where you're working on audio, where you're working on things where the data does not come for free, because you have to have people go and annotate it, right? You got to go say like, oh yeah, here's like a box around this car, or like here is this audio clip of someone saying yes versus no. Now you kind of have to go and get people to annotate this to get training data for your models. And also you have to go look at the models themselves, and you realize that deep learning models don't really need that much tuning as much as like you kind of used to have to do with like logistic regression and scikit-learn. So you can pretty much take something off the shelf, like a pre-trained model that someone at like Facebook AI research has done, and they've gone and made it really good and state of the art. It's hard for you to beat that, and then you can basically just go and make that work, and it like performs pretty well off the shelf. So now most of the work is not on the model side, because that's pretty good. It's actually now on the data sets. And so in terms of if you want to improve your models and to iterate on your models, then you mostly work on the data. Most of the sort of problems with the model performance can be traced back to, okay, like, the annotations on this data were incorrect because, say like someone was not trained very well when they were doing the annotation. Or the flip side is that maybe that you have underrepresentation of this like rare edge case that your model hasn't really seen that much in the training set, and then it goes out into production and it doesn't know what to do, and then it performs badly. So that's interesting because like, when I was working in the self-driving car world and having seen like, kind of working on structured data like Khan Academy and Pinterest, and now going to working on the sort of like imagery and audio and whatever like 3D LiDAR stuff that we were doing self-driving, you have these very stringent performance requirements. You need to be able to see a lot of things in a lot of various conditions in order for the car to not hit them or to get to where it needs to go. And so you got to make these models really good. And if you want to make these models really good, the best way to make them really good is to iterate on the data sets. And if you want to iterate on the data sets, you're going to need a whole new sort of set of tooling that people really didn't have back when we were getting started in like 2016 or so. So we basically built something at Cruise that works really well in terms of enabling this workflow of understanding where your model and your data were insufficient, and then going and taking corrective action based on just curating the data set. And as you improve the data set and then you just retrain the model, then the model kind of just gets better, and it's all kind of fine and dandy. And even better is that since you can kind of work on this data without having to do that much work on the model, you don't really necessarily need to have the ML engineer in the loop every day. You can have an operations person go and inspect the data, inspect the model performance, make the right changes, and then you go and you have a better data set, and then that turns into a better model. And so you kind of need a good tool chain to make this work. And a lot of people in the self-driving field, a lot of people who've been doing a lot more sort of applied AI stuff have built stuff around this, but there's still not really something that's super available that helps people understand their model performance and iterate on the data sets. And so that is what Aquarium builds. We build a product that allows you to enable that workflow and make it really easy for you to improve your model performance. So I'm just gonna pause right there. Let's look at chat. Is there anyone that has anything they would like to ask before we get started? Any sort of use cases that people are interested in, or just go into this? Going once, going twice. Okay, cool. So basically, I'm going to show you all Aquarium and just go through kind of a nice, normal kind of example set that basically is based on cats and dogs. So in this case, what we have basically is a classification task. And in this case, we have imagery of cats and dogs, and you gotta classify what what class it falls into, what type of cat or what type of dog. And so when you get started with Aquarium, what you can do is you can start with uploading your label data set, which is your imagery in this case, plus the sort of metadata and the labels on this imagery. And then you can also upload the inferences from a model that you have run on this data set, and you want to kind of analyze its error cases. And then once you get into Aquarium itself, now you can kind of understand what does your data set look like, what do your model inferences look like, and start to kind of dig deeper into what you need to do next in order to make your model better. So in this case, as you can see, we have all these nice pictures of doggos and cats, and then they have some labels, and then they have some predictions from your model. And so you can actually click into an individual data point and understand, what it looks like up close, and you can zoom in and zoom out if you need to. But you can also see sort of the metadata that is attached to this row. So for example, you can tell there's a piece of metadata here that just says that it's a cat versus a dog. And to show that is in the train test, in the train set instead of the test set. And you can also go and see similar examples in the rest of the data set if you want to find more examples of something like this. You can also go and filter. So for example, if you want to go say just show me all of the cats or something like that, or show me all the dogs, you can go and say, show me all of the dogs and filter down the data set just to this subset of things that you're interested in. And basically use this to just explore your data set and eyeball your data set to become one with the data. And so this is just kind of a nice visual way to go and do that. But you can also kind of zoom out and understand the distribution of the data inside of your data set and to understand kind of on the aggregate what it looks like. And so one example that is very common is seeing the class distribution. What are the classes in my data set? What are the labels in my data set, and how common are each of these different types of classes? So you can see in this case, we have a bunch of different classes of cats and dog species, and they're all relatively similar in terms of their distribution, which is pretty nice. And if you go and kind of look at the train test split, you can see that it's a fairly normal distribution across train, val, and test. And you can actually see on the metadata, you actually have, even though you have this sort of balanced class distribution, more of those classes are dogs than they are cats. And so maybe this is something where you may want to go collect more cats to offset it. So this is all kind of interesting, first off, but now you want to get into the interesting stuff of like, cool, like how do I actually improve my model? And the sort of key insight with our previous experiences is, well, if you want to improve your model, look for the places where the model disagrees with the labels. And so we can actually go into Aquarium and see kind of like the normal scikit-learn style, like classification report and confusion matrix, and kind of just go and look for basically the places where the model does the best or does the worst. But in this case, we can also look for a specific class of interest. Maybe we're interested in Shiba Inus, and then we can actually look at all the confusions and look at the places where the model got this class wrong and sort them from kind of like the most confident mistakes, like the highest loss examples, to the sort of low loss examples. And so in this case, we see that there's actually quite a bit of places where there's confusion between two similar types of dogs. The Shiba Inu typically has an orange coat. And in most of the cases where the Shiba Inu pictures show up, you can see they do indeed have orange coats, and the model does pretty well on them. But in a certain minority of cases, Shiba Inus have white coats, and they get confused by the model with another species of white dogs, which are specifically these like Samoyeds, except Samoyeds are much fluffier, even though they still have white fur. So this is kind of like a good way for you to discover, like, okay, well, this is a scenario in which my model is messing up on a particular subset or edge case of data that I should probably go address. So you can actually go and select all of these things and add them to our issue tracker, and then go and use that as a basis for resolving these problems with your model. But another sort of type of issue that we see is one of labeling mistakes. And so if we look at this pug class, for example, and we go sort of look at its like, highest error case of confusions, when you actually sort the confusions from kind of like the high loss to low loss examples, you actually see that a lot of like the high loss examples are cases where the model is actually correct and the data set is wrong. The labels are wrong. And it turns out by looking at these places with like, the highest disagreement, you can expose a lot of these error cases in the underlying labels. And so you can actually go and like, fix these problems and then get a cleaner data set for you to look at. So in this case, as you can see, this is actually a boxer, but it's being labeled as a pug by whatever annotator looked at it. So that's all well and good. Of course, we can add that to an issue. But the sort of interesting secret sauce of what Aquarium does is in dealing with neural network embeddings. And so if you were to think about kind of the flow of analyzing your model failures, you don't really want to look through the entire list of all the different failures, and it's just like a giant grid of images, and you spend a few hours looking through it trying to like find what is wrong with your model in terms of the sort of patterns or error cases that are kind of endemic in the data set. And so what you can do is you can actually group this data set based on similarity. Like, let's go and look for similar types of data, or look at similar types of specifically failures. And what we can use is this thing known as a neural network embedding. And an embedding is basically something that you can extract from like these sort of internal activations of a neural network that allow you to understand what data points are similar to each other based on like, the sort of pattern of activations, or different from each other. And this is nice for being able to find, okay, here's a cluster of very similar points of all these like, very cute Scottish Terriers. And to be able to find outliers in the data set that may be anomalous, or that may be interesting for you to go and take a look at. And so we can take these like, embeddings and put this into this nice 2D visualization where you can see kind of clusters of similar data, and find the sort of outliers of data, and see particularly floofy Newfoundland dogs, and just kind of explore the data set. And this is cool just for understanding the overlying, like distribution of your data. But you want to really actually focus your attention on the places where the model and the data disagree. And those are basically places where something is wrong. The data is wrong, or the model is wrong. And so we can actually color this cloud based on the confusion of the disagreement between the models and the data. And when you go and you basically only look at the disagreements, you can start to find error cases where there's kind of clusters of failures. And you can even just visually triage them based on the density of the failures. So if we were to look at this, sort of cluster over here of failures, we actually see that, the model just consistently does not perform well on certain types of black cats. It just gets them wrong a lot of the time. And this is just a really easy way for you to be able to like go and immediately uncover like here is a place where the model is consistently messing up, and then use that to triage this issue and then go and take resolutions. So of course we can go and add this to an issue like before. And then once you get into the issue tracker, this is kind of the sort of interesting part where you can start to take like actions to fix these problems in the data and then go and retrain a better model that is therefore better. So in this case, where we have, for example, this Samiyed and Shiba Inu problem, this is something where this is actually a model issue. Like, this is something where the model is wrong and the labels are right. And so what we can actually do is go and look at similar examples in this data set to see if there are more cases that are like what we just found inside of the data set. And you can actually find that there are cases where you have white coat Shiba Inus where the model actually predicts it correctly. And then you also have cases where like the model is actually correctly predicting Samiyed, but they all look quite similar. And then you can also see this kind of stuff where there's like white Chihuahuas that have like the same like, sort of fur. And you can actually use this as a way to understand how prevalent this problem is in the data set without having to rely on searching with metadata. This is purely using similarity between the underlying content of these images alone. But the other interesting thing you can do then is to not just search within your data set, but also to search within your unlabeled data to find more examples of this edge case for your model to train on. If your model is kind of messing up and getting confused on these sort of scenarios, well, you maybe want to go collect more examples of the scenarios so that you can put into your data set and retrain your model, and hopefully it will do better. And so what Aquarium helps you do is set up a collection campaign where you can basically go look through an unlabeled data set and then go and find more examples that are similar to this edge case that your model struggles on. You can use this embedding search to bring them back and basically get it labeled and then retrain your model and then see that the model gets better. And so by having this entire workflow encapsulated in this nice like web app that you don't really need to write any code to use, this allows someone who is not an ML expert, but maybe like a domain expert who knows how to distinguish between 100 different types of dogs and cats, to go and work on the data set, improve the data set, and therefore improve the model. And so that's the kind of workflow that we try to enable, and this is what Aquarium is basically built to do. So we help people ship better models faster by iterating on the data set and producing better models. So I just want to pause for a second and get people's thoughts. We have an hour and a half here, obviously, and that's quite a bit of time. And there's a lot of stuff that I can show in terms of the feature set or various use cases. We support things like audio. We support things like 3D point clouds and NLP stuff. But I'd love to just hear if anyone has any questions or thoughts that they would like to go through. Anyone here? Type in chat. All right. Well, let's see. I'm curious. Like, what do people here do? Like, what do you all work on? I'm curious. Shashank and Nikita, what sort of tasks, problems, or whatever do you work on? Regarding the embedding, is there also an option to do model-based embeddings? So I'm not exactly sure how to interpret that, because the embeddings that we use by default are generated using a pre-trained ImageNet model. So that's like basically we run this pre-trained ImageNet model on a piece of imagery or audio or whatever, and then we can generate an embedding that is a sort of sane default in terms of understanding the similarity or the clustering or the outliers in the data set. However, we highly, highly recommend, as soon as we get started with a customer, they start using the embeddings extracted from their own models. And the reason why is because when you train a model on a data set, it's going to have kind of more exposure to the data, and it's going to be able to kind of construct this internal understanding of what is important for it to be able to accomplish its task. So we highly recommend that when we get started with users that they extract and upload their own model embeddings. And we also provide a guide for how to extract the best embeddings from sort of a variety of sort of common model types. So yeah. And cool, yeah, Nikita, great to hear. Yeah, so basically, Shashank, for what we are doing, this is something where we are starting with essentially activations from the middle of a model. And then we are, first of all, like collapsing it down into 2 dimensions using UMAP. And that's what generates this nice visualization here. And that's really good from the perspective of a human analyst who wants to go and find patterns or correlations or like outliers in the data. And that's nice, because it's so understandable. But then we also understand that if you have this sort of like, input, embedding that is like, say, 1,000 dimensions long, and you're sort of like crushing it into this 2D visualization, you're going to lose information, right? You're essentially like, making trade-offs to try and capture either like the global or the local structure when you're doing this visualization. And so when you actually are doing the searches of like, the embedding similarity searches or like, other sort of stuff where you kind of want like, better understanding of similarity, we actually do it in more like, the full dimensional embedding space. So that's a little bit less lossy. So you kind of get the advantage of the human interpretability, but then you also get the sort of like good precision and recall of using the full embedding space. Yeah, no problem. And like the thing that's really interesting to me is that this is something where I feel like people in certain kind of like big industry labs have already kind of figured this out. Like if you go and look at Waymo, they have this thing called content search that they use for essentially active learning workflows, and they've already figured it out internally. You go and you look at Entree talk about the Tesla system. They've already done this for like the stop sign sort of like mining, where they have like difficult cases of stop signs and they need to go collect more cases of stop signs to retrain the model on. We had done something quite similar at Cruise in terms of setting up this active learning pipeline. And you can go see, there's like a blog post from Tinchi Gao where he talks about some of that work. And then, there's kind of like, Pinterest, where they have this system called Voyager, which kind of like is also kind of the nice UI for being able to go and, curate your data sets. So like, Aquarium is kind of like taking a lot of these ideas and concepts that, people have already applied inside of these giant companies and already know that it works, and just trying to bring it out to people who are, not as far ahead in terms of like having like 100-person machine learning infrastructure teams to help them ship some better models faster. But on the research side, I think it's interesting. You spend a lot more time on the models. And when you're on the industry side, you don't want to spend any time on the models. You want to just rip something off from like, the Keras examples repo and just work on the data. So nice to see you again. Did a little talk for full stack deep learning, and I'm just excited to be here and get the word out on what we're trying to do. But that's kind of the big thing that we try to emphasize, which is that, hey, most of the time, like, you're not going to get a lot of gains from doing some like crazy grid search on your hyperparameters. A lot of the time, you just need to go look at the data. Like even if it isn't using Aquarium, just go use your file explorer, go use a spreadsheet, go use a Jupyter notebook, and just inspect the cases where you go wrong and try to build some intuition about what's happening. Because I have seen so many cases where you train a model and you're like, oh man, like, it's not doing so well. And then people kind of like blindly go and try things and throw stuff at the wall and see what sticks. But then when they actually go look at the data, they realize like, oh, well, half the labels are garbage. So of course the model's not going to do so well. And so the highest ROI thing there is just to go fix the data before you go and like think too much about fancy stuff on top of it. If I were to talk about, there's kind of like a Maslow's hierarchy of applied ML, like the basic thing is like, do I trust my data? Do I trust that it's clean? Do I trust that it is consistent and accurate to my expectations? And then once you do that, then you can trust your metrics on top of that data. You can trust your accuracy metrics and be sure that it's not lying to you. And then you can go look at, okay, well, here are the places where like my model and my data is disagreeing, and kind of like, find the sort of clusters of edge cases where my model really struggles. And then once you kind of go and do kind of like targeted data collection or active learning to solve those sort of like edge cases where the model doesn't do so well, then you can go and start looking at the places where you have examples that are showing up in production and they're not represented in the training set, so the model doesn't know what to do. And so once you get sort of these three steps of Maslow's hierarchy of ML, then you're in a pretty good spot. But most people don't really get through the first or the second. So that's kind of what Aquarium is trying to help people do. It's trying to shepherd them through the shining path of making really good models just from focusing on the data. And then, once you've gotten through all that stuff, then you can go and, examine new architectures and whatnot. So, label errors on GitHub. Use this. Oh yeah, there's a lot of label errors in open source stuff because it's just open source stuff. Like you don't really have like a team that's like working on maintaining it, which is kind of a shame. But that's just kind of how the way it is. That's something where people who are working in research are trying to optimize for like here's like a 1 to 5% gain in performance on this data set, and then they don't realize that the reason why they're getting 1 to 5% gains are because like there's labeling errors in the underlying data set, and then they're just kind of like getting like slightly better on this thing that is not super trustable in the first place. And you can see this especially with like massive data sets like ImageNet and stuff, where it's just inevitable that there's going to be some labeling errors that creep in. Yeah, so I see people who are kind of like dropping in and out in terms of seeing what's going on here. I'll just also quickly go and show you that we also do stuff like audio. We do stuff in 3D sort of point clouds and stuff. And the sort of interesting thing about that is that, the only thing that really changes is the UI aspect, right? Like, if your task is the same, you're doing classification in imagery versus like in text versus like in audio, then you just need to render something different on the UI side in order to get the same results. And the thing that doesn't really change is the fact that you are using embeddings, and neural network embeddings can be extracted from pretty much every neural network. And so you can essentially get this learned feature vector for free, and you can apply this in a very general way across a lot of different tasks and a lot of different problems. And so for example, in this case where like this task is like you get an audio clip in and you want to predict what someone is saying inside of it. Well, you can also go and plot out the distribution of the data set, see kind of like where there's outliers, where there's sort of like clusters. But then when you go and color by the sort of confusion, like the disagreement between your model and the data set, it's exceedingly clear that the places where the model and the data disagree are places where you essentially should not have this data in your data set at all. If you look at this stuff, it's all places where the audio clip is basically malformed. It's like places where the speaker is supposed to say off, but then they barely start speaking before the end of the clip. So like in this case, they say forward. They're supposed to say forward, but then all you hear in the actual audio clip is just full. And so the model can't tell what the hell's going on there. There's no way the labeler can tell what the hell's going on there. And this is kind of just like a quirk of the labeling process that's exposed in the data set, and it's basically messing up your model performance. So this is the type of stuff where like you start off and you're like, I was doing this as an example, and I was like, oh geez, maybe I should go like try like doing like a convolutional model on this, and instead of doing like a 2D convolutional model instead of a 1D convolutional model, oh, I should try this hyperparameter, oh, I should try augmentation. And then you look at the actual problems in the embedding space, and you see they're all clustered into the same thing, and the same thing is this endemic data problem that is nothing to do with the actual model itself. Like you just have all these problems where the data set has like nobody speaking in these clips at all, and yet they're not labeled as such, or like someone is just starting to speak at the end of it, and it's essentially like is a product problem with the data. So yeah, I mean, like that's the sort of intelligence that we hope to give to people in terms of just error analysis, and then give you like a really easy means of going and adding this to an issue tracker, and then using that issue tracker to go and basically take resolutions that will improve your model performance. So, well, cool. I mean, yeah, like anyone else want to chat? I'm here for until 12:30, but if we've got just the three folks in the room, I'd love to just hear if anyone has any thoughts or think they have stuff they want to discuss or anything like that. But, yeah. Going once, going twice, going thrice. All right. Well, I guess that's it. In terms of if anyone wants to check out our stuff, feel free to check out our website. I'm going to post that in the chat. And if you'd ever like to talk more about machine learning, or if you want to talk about some of the problems that you're facing in your current job, and see if there's any fit for us to help out, then you can always reach out to me personally and shoot me an email, and we can set something to chat. But thanks so much for dropping in, and hope to see y'all soon. All right, see you later.